Okay. So, yesterday I went through omega extremely fast. I said, yeah, there is this operator, and it does this and that. I wanted to stay a bit longer on omega today. So, this is from Partition Theory Memoirs. And this is McMahon. So McMahon says, suppose we have a function f in two sets of variables z and lambda, which can be expanded in ascending powers of z. Such an expansion, being either finite or infinite, the coefficients of the various powers of z are functions of lambda, which in general involve both positive and negative powers of lambda. Now, we may reject all terms containing negative exponents of lambda, exponents and subsequently put lambda equal to 1. Okay. Now, thus we arrive to a function only in z. Which after Kelly we denote by omega of f of z lambda. So, and we can also use omega equal, which would be that the powers of lambda must be equal to 0. Okay, this is exactly what I said yesterday, but in written format so that it's more clear maybe. This is the definition of the omega operator by McMahon in Partition Theory Memoirs. Now, let me do again let's say we have the system this linear Diophantine system. So this is a linear system where well, that's square, 0 included in natural numbers. And from this we defined a crude generating function, which is this multi-sum expression where x and y is non-negative, and we introduce one variable for each inequality, right? And we have x minus y minus 1, and then a new lambda variable for the second equation or inequality, so 2x minus y minus 3, and then to keep track of our variables, we have this. So this is the multi-sum version. And we said that by using only the geometric series expansion formula, we can arrive to this rational function. Okay? And yeah, so then the question was, what do we do with this? Sorry. Yesterday I mentioned about the partial fraction decomposition of Elliott, which McMahon used in order to have an algorithmic solution, an algorithmic version of computing the omega operator. So partition analysis is about applying the omega operator on such for such problems that actually represent integer partitions. So, and then I said that, okay, he had the general method, but even McMahon, which already we heard a couple of times how great a computer he was, like computing P of 200, that's something. Still, he didn't want to compute this, evaluate this by hand using Elliott's decomposition. So he developed some rules. For example, this is the first McMahon rule. It says that omega of 1 lambda x minus lambda x times 1 minus y, the lambda minus s. Let me write it directly like this. This is what? This is 1 over 1 minus x times 1 minus x to the s y. Okay, so now why is this true? Well, we can do we can prove this. It's not hard to prove. But what's even nicer is to draw it, right? So now we can draw such things. So here we start in 3D, right? Well, always we have to check that this rational function is the rational function for the lattice points in a certain cone. Is it? Yeah, it is. So what are the generators? The generators are 1, 0, 1, and 0, 1 minus s, right? Okay, so one. Anyway, so this is my 1, 0, 1 vector. Colors. And then I have the 0, 1 minus s. And it would be something like that, right? And now I have a cone here, right? And what do I want to do? I want to eliminate, I want to keep only the things that have a non-negative lambda coordinate, right? Okay, this cone, where since one generator goes above the xy plane and one goes below, obviously it has an intersection with the xy plane where lambda is 0, right? So it is this vector here. And what is this vector? So the lambda coordinate is 0. And what is the first two coordinates? What's the simplest vector we can find? S and 1, right? So this vector is actually on the intersection of the cone with xy plane. Okay, and now what I want is this, right? So what I want is a cone generated by 1, 0, 1, S1, 0, right? And what is the determinant of this? This is 1, or minus, it doesn't matter. It's okay, so from this I can conclude let's call this C. The rational generating function of C is what? So in the denominator we put down to, yeah, actually, sorry. Yeah, so we first take things that have no negative exponent, and then we set lambda equal to 1, right? Which means we project to the xy plane. So now this, we will forget that, and we will forget this one as well. Actually, then the cone we have is the cone generated by 1, 0 and S1. So this I actually didn't really need. So I have the cone 1, 0 and S1. Okay, and what is the rational generating function of this cone? The determinant is 1, so the numerator is 1, and the denominator is 1 minus the first generator, which is x to the first y to the 0, and the second is x to the s, y to the 1. Right? So I go once more through this, what we did. So we check the function on which we want to apply the omega operator. We notice that this rational function can be the rational generating function of a cone. What is this cone? Well, we check the denominators. The denominators tells us that the generators would be 1, 0, 1 or 0, 1 minus s. Okay, so this blue thing is our cone. These are the generators. Now we want to eliminate lambda. We want to get rid of lambda in the end, right? How do we do this? We say we want to reject all terms containing negative exponents of lambda, right? This means forget anything that is below the xy plane where lambda is negative. So I find where is the intersection of the cone with the hyperplane, and I forget what is below. So now I keep the cone that remains above. What is this cone? This cone is generated by the vector we found in the intersection and the vector that was going above, right? So now this thing here is all above the xy plane, so the lambda exponents are non-negative. Okay, and then it says put lambda equal to 1, which means we forget the coordinate. We have to project, orthogonally project to the xy plane, right? So we take this 1, 0, 1, and we make it 1, 0, and the S1, 0, we make it S1. So now our cone is generated by 1, 0, and S1, and we want to compute the generating function for the lattice points in this cone. How do we do this? This is a simplicial cone, by the way, okay? In 2 dimensions, all cones are simplicial. So since it's a unimodular, the determinant is 1, the numerator is 1. And in the denominator, we put the 1 minus z to the generator, right? So 1 minus x times y to the 0, and then x to the s, y to the 1. These are our generators. Done. Okay? So applying the omega operator on this function gives us that. That's McMahon's first rule. Hope there are no objections, so I can move to the second McMahon rule, which says by the way, that's pretty simple, right? So the second one says lambda 1 minus lambda to the s times x. Let me write it properly. X lambda to the s times 1 minus y to the lambda minus 1. Okay?
Sam, can you pull up the first word just a little bit?
So, are they very different? I mean, okay, so here we had the s, instead of having it in the minus, here in the second term we have it in the first, right? What do we expect the answer to be here?
This can be anything.
Sorry?
This can be anything.
It can be anything here. I mean,
there is no bad words.
there is. I mean, what do you mean there is no bound? Okay, there are infinitely many points in both cones, right? This is also a cone, by the way, but as we will see. But the answer to this is this 1 plus x times y times 1 minus y to the s minus 1, 1 minus y, 1 minus x, 1 minus xy ds. The answer doesn't look very similar to that one. That looked way nicer, right? Okay. Let's see what happens here. What are the generators? Now we have 1, 0, s, and 0, 1, minus 1, right? So 0, 1, minus 1, we have this one, and we have 1, s. Okay, that's a very bad drawing. So our cone is here, and we'll play the same game. We will find the intersection with the xy plane, and yeah. Yeah, so this time this will look more like this. And now our new cone is this one, which is here this would be the 1s0 and 103, this 10s. Okay? So if I project now, what I get is 1, 0 and 1s. Funnily enough, the determinant of that is not 1 anymore, right? Finally, we will see, after 3 days, we will see a non-unimodular cone. So if I project this cone on the xy plane, what I will actually get will look, so it is 1, 0 and 1s. Now, where is my fundamental parallelepiped? Actually, yeah, I drew it very badly, no? Yeah. It is 1, 0 and 1s. So here, I have actually a number of lattice points. How can I draw so badly? Anyway, we will see these points because we can see it here, actually. So I can tell you what exactly are these points. So we have the origin, which is here, right? Maybe I could do it easier. And 1s, right? So this is what we have. This is 1s, and this is 1, 0. Just forget about that one. So now, let's see what happens. The origin is a lattice point, and this is this one that appears there. And can we find what is the rest? So what other lattice points we have? We have 1, 2, 1, 3, 1 up to 1 till s minus 1, right? Okay. What is this? Sorry?
1 plus y plus y squared over the 2 s.
Exactly. So this is a finite geometric series, right?
X times y.
Sorry?
X times y.
Well, not yet. Yes. This part, right? So that's a segment geometrically. So we have a segment, which is this segment here, right? This is the finite geometric series, which appears here. And then, yeah, so this doesn't start from 0. It starts from 1, 1. And that's why we multiply with 1, 1, meaning x times y, right? And that's how the second McMahon rule can be seen geometrically.
Are you missing a plus 1?
Here?
Yeah.
Why not?
And the end is s minus 2.
Is it? Yeah, okay. Yeah.
Didn't you multiply it by y?
Not yet. I multiply it later here. So this blue thing is that. Okay? So, okay, this is the interpretation of the second McMahon rule. By the way, now, when I first saw this, I was kind of annoyed that although the original thing looks quite similar, right, where we apply omega, I understand the difference, but it looks very similar and the result looks very different. But if you see the geometry, I mean, the moment you compute the determinant, you know what happens with the numerators, why they're so different. Okay. Questions?
Can you just remind me what is the second rule? I'm a bit lost.
So the second rule just says if you have such a crude generating function, if it happens to be of this form, then the result is that. Okay? That's it. By the way, you can hide in x and y whatever you like. It can be many, you hide many variables. But it says if it happens that the exponent of lambda is some positive number, and the exponent of lambda in the second term is -1, then you can directly write the result like this. So McMahon, instead of computing, applying the algorithm every time, he came up with certain rules that I think it's 12 or 14, which allowed him to solve whatever partition problems he was interested in. Well, except for one. Yeah. He was very interested in that one, but he didn't manage. So, yeah. Now, I have this amazing system, linear Diophantine system. It's a bit small, I agree, but we want to eat cake, so I will stay with small examples. How do we solve this? We need nothing that is not on the board. So this is the system, right? We're here. So yeah, alpha, so A is 1 minus 3, and B is 0. Boring, but yeah. So from there, we move to the multisum, but I will just jump one step. And now what we want is to compute the omega on this crude generating function. So we have only one equation, so I only need one lambda. What is the right-hand side? B. It's 0. That's good. And then we need to construct these terms, right? So then we will have Z1 and, okay, actually I will do the multisum. We want x and y such that, so non-negative, such that, so we have lambda to the x minus 3y, z1 to the x, z2 to the y, right? How do we write this as a rational function? We want to apply omega on that. So we have 1 in the numerator, and in the denominator, if we gather together the things for x, we have 1 minus z1 lambda, right? And 1 minus z2 lambda cube, lambda minus 3, sorry. Okay. Good. What is this? Equals? Hmm? 1 over 1 minus y? Or is it 1?
Z1.
Okay.
Z2 3.
I think it's like this. So that's the second rule, right?
No, the first one.
It's the first rule? That's the first rule even. Good. So this is how we apply the rules, right? So we wanted to solve this system, and we just got the answer. Shall we convince ourselves that actually this is meaningful? Yeah, probably. So if we expand this, what do we get? So this is no. What? Am I correct? Yeah, I suppose. So the points we will get, if we start the first, is this correct? It is 0, 0. I will just write the exponents now. 3, 1, 6, 2, etc. Right? And then I will take Z1, and it will be 1, 0, 4, 2, whatever. No, it's a. Seven, 2, 8, 3, etc. Okay? And indeed, these are all the points we can see that where the second part is at least 3 times larger than the first. Good. Okay. Yeah, I don't think we will have cake. So, okay. Questions?
So you meant to say the first part is 3 times larger than the second part.
Yes, right. That's what we say here, right? Okay. So I will show you tomorrow probably a diagram of how the method was developed historically, but essentially the next big step is the essential big step is Andreas Paul-Leris coming up with a better partial fraction decomposition. Okay? Yesterday we said that McMahon used Elliot. Elliot is a 3-term recurrence. We took one rational function and we split it into 3. Okay? But now Andreas Paul-Leris say, no, we have a better one. So you see, I usually don't like to write a lot of things, but in this audience, I don't think this is a problem. Oh, no. No. So, okay, it is a 2-term recurrence, okay? Obviously better in terms of complexity. So it says if you want to apply omega on a rational function of this form, well, the result is this one, okay? So the question is, what is these two polynomials appearing here and there? And this polynomial is for I 0 to alpha minus 1 of AI lambda to the I, where AI is minus x to the beta y I over beta if beta divides I, or if I equals 0, and minus x to the modular remainder of a certain term otherwise. And the second polynomial is actually quite similar. Okay? So, now why this? I have asked actually, so I asked Peter Paule, and he told me to ask George Andrews why these are these polynomials. And I asked George Andrews, yeah, because they are, right? They work. So, I mean, I mean, this is a pure genius to figure out that these do the job, right? So, he came up with this form, and it works. Okay, but since due to lack of genius, I will follow the geometric perspective, and I will show you what this mean. Yeah, by the way, okay. So here we can expand this, right, and multiply this out. Okay? And again, we have two rational functions which we would like to interpret them as rational generating functions of cones. But this time, it's not that obvious that this thing. So what is it? It's 1 minus and So why is this a cone? Not that obvious anymore, right? Okay, by the way, I forgot the conditions. We want alpha to be greater than beta, greater than 1, and the GCD to be 1. These are technical, not extremely important. They don't, I mean, they're important for the proofs, but without loss of generality. So, okay. Now, my personal hell, I have to draw in 3D again. So, what do we have here? Sorry, what I wanted to draw first is this one, right? Where both alpha and beta are positive. This is what we start with. So let's say we start with something like that. Okay? Now, let's take the hyperplane that this cone defines. This is a two-dimensional cone in 3D, right? So it defines a hyperplane, and let's take the intersection of this hyperplane with the xy plane. It's the same game we played for the McMahon rules, right? So we will find some vector here. So this is the intersection of the hyperplane defined by the blue cone with the xy plane. Okay, now let me take this cone here, yeah, right? The orange cone, and the red cone. Because what is this point, this vector? This vector is that vector. This one, right? So this says, it is this one, right? The intersection of the cone generated by 1, 0 alpha and 0, 1 beta is the point, is the vector beta minus alpha 0. This is in the intersection of both hyperplanes, right? We just multiply with the last coordinate. It's cheating, so it works. So that's the vector we have here. Okay, and I say take this new vector you computed, once with the one from the old ones you had, and once with the other. Okay, and we have the orange cone and the red cone. Clearly, the blue cone is the difference of the two, right? So, okay. What is it? Orange first. So the orange cone is a fat one. Okay? And guess what are the lattice points in the fundamental parallelepiped? Well, Andrews Pauli geniuses, right? So these things here are exactly, these exponents give you exactly the lattice points in the fundamental parallelepiped of this cone. I know nobody will trade cake for this proof. It's a boring one, but it's done. And the same is true for the red cone, where the fundamental parallelepiped is given by Q. Just one thing, actually. No, it is here. Yeah, right. Is this P, am I right? Then P is the smaller one, because these minus signs are exactly in order to get the No. This is fine. So I was trying to figure out where we get the difference, but the difference we get when I take this and make it like that, I pull out a -1, right? So one of them becomes negative. How does one of them has to become negative? These are exponents though. No, they're not. Okay, probably it's from here, because here I don't have minuses actually. So one of them is negative, the other is positive, that's a difference. So what was extremely interesting for me is that there is a detail here, okay? When I say orange minus red, if I actually say this, I lost this face, right? So actually, this red cone should be open here. Guess what? Taken care of from these polynomials. Okay? So really, what this partial fraction decomposition is this cone decomposition. We take the blue cone and we decompose it into orange minus red. Okay? So, questions?
Is this the proof they use, the geometric proof?
No. That's actually, so this is 2000 something, 2000, early 2000. It's not 99. This is the sixth. Okay, there is a partition analysis series papers, which now is at 13, as we heard today also, right? But so this is 6. So this is actually, I'm sorry, this is 3. So this is 3. This is the first version of partition analysis they gave in this. And this is implemented in the Mathematica package Omega, which I don't think is available, because in partition analysis 6, they gave a better one, which is called Omega 2. Okay? So, yeah, but this is my PhD, essentially. So the geometric interpretation is about 10 years later. Which doesn't sound that much anymore, because it's also 10 years from now, which is a bit frightening. Yeah. So I'm not going to go to the, okay, now we saw the geometric interpretation of Elliott, of McMahon rules, of Andreas Paul-Lerische. Okay, we have a good understanding of what partition analysis is doing, right? So we essentially set up a system with this trick of introducing new variables, right? The lambda variables. And then we do some kind of elimination, and we want to compute the generating function for whatever remains after the elimination. Okay, tomorrow I will say this without caring about any particular decomposition, right? Because we actually have an amazing tool for decomposing polyhedra, right? Brion's decomposition. So if we can find a Brion decomposition, I don't need to come up with such formulas. I just need to know to have a Brion decomposition. This is the same as this, for example. Well, not really as this. This is a cone decomposition, but the idea is the same. So now, instead of doing recursively decompositions, we will do it all at once. And this is not coming from partition analysis. This is coming from polyhedral geometry. But what comes from partition analysis is that in order to be able to do this polyhedral geometry easily, we will exploit McMahon's trick that we introduce new variables. And we will do something that people in geometry don't want to do, go to higher dimension, right? For every equality, for every equation, we introduce a new variable. That's terrible. It's new dimensions in geometry. But at the same time, it simplifies the geometry. And this is why tomorrow, in less than half an hour, I will explain how to do all this at once. And I'm not going to continue because cake is here, right? Yeah, okay, thank you.